Good day, students. Now, today we're going to be looking at the physics of the atom. All right, so we're going to look at that part of the syllabus, and what we're going to start with is by looking at the structure of the atom, right, of a simple atom. Now, what we have behind me here is a diagram showing the structure of the 10th element. And what we're going to see here is that an atom, what we know is like the building blocks of all states of matter, is one of the smallest known particle. Is the smallest known particle to man. Now, what we want to understand is what makes up an atom. Now, we can start by first looking at the nucleus of an atom, which is the centermost dense point of an atom, right? And the nucleus itself contains it contains protons and neutrons, where protons are positively charged particles and the neutrons which have no charge, right? Both are found within the nucleus of an atom. Now, what you're going to realize in a few minutes, you're going to see the importance of the neutron inside of the nucleus. Because what we would have learned based on the properties of electric charges are that positive charges repel each other. Now, if you have protons by themselves within the nucleus, we expect all of these protons to repel each other and break apart the nucleus, right? So they will be very strong in intermolecular force in the nucleus. Now, with the presence of the neutron in the nucleus, you're going to realize that we don't have this type of strong repulsive force between the protons, right? So for up to the 30th element, you would have equal number of protons and neutrons inside there. And what happens is that the protons are attracted to the neutrons, right? Positive charges are attracted to an uncharged body, basically. But now, on the outside of the nucleus, you're going to have energy shells. And on these energy shells, you're going to have electrons, which are negatively charged. And these electrons orbit around the nucleus, just like as the textbook will describe, just like the way planets orbit around the sun, right? So even though they are negatively charged, you find that the electrons are moving so fast that and they have a bit of force, a bit of energy basically, that they would not fall into the nucleus or be attracted into the positively charged nucleus, right? And in reading, we realize that you will only find 2 electrons on the first energy shell, and then you can have a maximum of 8 electrons on the second energy shell, and up to well, not in our syllabus, but in advanced physics, you find a maximum of up to 18 electrons in the third energy shell. But at this level, we only focus on the 8 electrons. Now, we're going to go a bit deeper into looking at the physics of the atom. Now, one of the first things that we must understand, other than the well, the structure of the atom, is to understand the importance of all the subatomic particles, right? And I quickly mentioned about the protons and the neutrons. Now, a neutron itself, first and foremost, is made up of equal amounts of a positive and negative charge. So basically, a neutron is a combination of a proton and an electron. Good? So therefore, those two charges cancel out each other. The positive cancels out the negative charge. So therefore, it has no charge, no overall charge. Right? Now, one of the things we have to learn how to do is the Nuclide notation. Is how to represent the nucleus of particular atoms in terms of science. And they follow a format. Right, so we have the nuclear notation here, which shows you A, Z, X, right? Now, it's a bit of chemistry, but we're looking at the physics aspect of it. Now, A represents the mass number, otherwise known as the nucleon number. Nucleon, right? Now, that word might sound strange to you, but what I want you to realize is that um, the proton and neutron are both found within the nucleus of an atom. They're both found within the nucleus of an atom. Now, it's just like saying if you come from the planet Mars, you're known as a Martian, basically. So, because you have protons and neutrons are present within the nucleus, they're also referred to as nucleons. Good? So, they account for the total mass of the nucleus, or the total mass of the atom itself, because the electrons are so small that their mass is actually negligible. They don't account for anything, as otherwise said. All right. Z represents the proton number, or otherwise known as the atomic number. Good. So it tells you the number of protons that are present within the nucleus, and what you can find out is that the proton number also lets you know which element you are in the periodic table. Good. Now, one of the things we're going to see here as well, the symbol N, capital N, denotes the neutron number. And the neutron number tells you the number of neutrons you have within the nucleus of an atom. Now, we can relate each of these symbols to find the mass number with a simple formula. That the mass number, as we previously stated, is the number of protons and neutrons within the nucleus. Hence, there is a simple formula to find the mass number where A is equal to Z plus N. Right? A equals Z plus N. Otherwise, I like to memorize it. I like to call it ASEAN. Right? So ASEAN. So A equals Z plus N. Now, this formula can be rearranged in any way to find any one of those unknown terms. If we want to find N, or if we want to find Z, we can rearrange this formula to find any of those unknown terms. And also X is the symbol, it's just a notation there that we can change it to represent any of the different elements within the periodic table. So in the case, if it is uranium, it will be capital U. Good? If it is oxygen, it will be capital O, and so forth. Now, to mention there, so we rearrange ASEAN, and we could realize that to find the proton number, it will be the mass number minus the neutron number. To find the neutron number, it will be the mass number minus the proton number. One of the things that we don't necessarily see, because this basically applies to the nucleus, is the electron number, right? E represents the electron number, and in most cases, what we're going to explain in a few minutes is that the electron number is the number of electrons. And how can we determine the number of electrons? It can also depend on the neutrality of the atom. In that case, what it means is that most atoms tend to be neutral, meaning as a neutrally charged, that is, that they have equal number of protons and electrons. So if they have 10 protons, they're expected to have 10 electrons. Otherwise, if they have fewer electrons than protons, it means that your element or your atom is now positively charged. It is now a cation. It now has turned into an ion, which is known as a cation, because it would have lost an electron. Good? Now, if it would have gained an electron, it means that it will now turn into an ion as well. And in this case, it is now known as an anion, right? Wherefore, it is now negatively charged. Good? So an atom can lose an electron, or it can gain an electron to become an ion. So otherwise, an atom will have equal number of positive and negative charges, the same number of protons and same number of electrons. Good? Looking at this example that we have here, I gave you a notation there. and it's actually uranium. So it's uranium 235 and 92. Now, what I have asked here is what is Z? Z represents the proton number. And so we have to know exactly where to find the proton number in this notation. And that's the number down here, right? That's the 92. So basically, so Z will be 92. A represents the mass number. Now in this case, we want to know what's the total amount of protons and neutrons, right? So in order to find A, we know that A is written to the top left hand side, so which is 235. 235. N represents the number of neutrons. Now, it is not given there in the notation. What we can see there is the mass number and the proton number. But we want to know how can we find the neutron number. And as I stated before, in terms of rearranging the formula, we can realize that N can be equal to the mass number minus the proton number. Right? So we have N is equal to the mass number minus the proton number, which will give us an answer of 143. Good. So it has 143 neutrons. Good. What about if I say that this is a neutral atom? What will the electron number be? And as we stated before, that the number of electrons equals to the number of protons. So hence E is going to be equal to 92. If you got that correct, give yourself a clap. All right. So now what we're going to look at as well is the stability of the nucleus of an atom. All right. Now, as previously mentioned, we're going to see that in the nucleus, it contains only protons and neutrons. Protons and neutrons, where you're going to have a very strong nuclear force acting there, right, between the protons and the neutrons. Now, we want to talk about stability, being stable, not being destructive, right? Because we don't want the protons pulling apart from each other and destroying. Now, what I have a statement here says that an equal number of protons and neutrons up to the 30th element results in a stable nuclei or a stable nucleus, right? So having equal numbers of protons and neutrons will always result in a stable nuclei, meaning if you have 10 protons, you must have 10 neutrons. You have 12 protons, you have 12 neutrons. Now, whenever an atom has more more neutrons than protons, it can become unstable, right? Or in a case, if it has too little amount of neutrons than protons, it can also become unstable. Now, beyond the 30th element, you're going to realize that you have more protons more protons present in the nucleus, and in this case, you will need extra neutrons or more neutrons than protons because the force of attraction between the protons becomes much larger, right? So the intermolecular force between the protons becomes greater, so you're going to need more neutrons than protons. But having too many neutrons can result in the instability of a nuclei. Now, when we talk about instability of a nuclei, we're therefore going into a term known as radioactivity, right? Radioactivity. All right, so now we're going to look at radioactivity. And as you can see there, it says that radioactivity is the spontaneous disintegration of an atomic nuclei by emitting radioactive particles, right? By giving out radioactive emissions. Now, as you will see in this syllabus, that it covers 3 different types of radioactive emissions. Now, those three types are alpha emission, which is an alpha particle. Then you have a beta decay, which gives out a beta particle. And then the third one is gamma radiation. So it's not a particle. In this case, it's a wave. It's gamma radiation. Good? Now, we want to understand the difference between each of these, right? So as I say, radioactivity is the breakdown of the atomic nuclei. Is where it decays, right? Or it dies. And so basically it was unstable, and in order for it to regain stability, it must give up these unstable particles, basically. So the first one is an alpha particle. Now, alpha particle is emitted, an alpha particle consists of two protons and two neutrons, right? So because it has two protons, we're going to realize that it is a helium nuclide. Good? It has two protons and two neutrons. So therefore, it is going to look like this. Right? Just remember what we learned in our nuclear notation. It's made up of two protons, and it also has two neutrons. So 2 plus 2 gives you 4. And because it has a proton number of 2, therefore it's a helium nuclide. So basically it's a helium atom without any electron. So it's the nuclei of a helium atom. So that's why it says a helium nuclide. Good? So anytime we talk about an alpha emission, it means that it gives out this. It gives out a helium nuclide. It gives out two protons and two neutrons. Now, one of the things, the properties of the alpha particle is that it can only travel a few centimeters in air, right? And what it says, it also has a charge of two protons, and it can be stopped by the skin or by a thin sheet of paper. Also, it has a strong ionizing power, meaning that as this alpha particle passes through other atoms, it can pull electrons off of their valence shells, and that it can be deflected by electric fields or by a magnetic field. So once an alpha particle enters the electric field, it can be deflected, and because it is it is positively charged, it will veer over to the negative electrode in a field. Good. The next one is a beta particle. And remember, something I must mention is that these particles are all emitted out of the nucleus of an um, unstable nuclei. Now, the beta particle is a fast-moving electron that is emitted out of the nucleus of an unstable nuclei, right? Or out of the nucleus. Now, when you listen to that definition, it says it's a fast-moving electron. How can a fast-moving electron be emitted out of the nucleus of an atom? Because we know that only protons and neutrons exist within the nucleus, within the nucleus. And now we're saying that a beta particle is a fast-moving electron. Now, the way this happens is because the importance of the neutron. Now, the neutron gives up its negative charge, and therefore the neutron is now going to turn into a proton. Good? So this negative charge that it gives up is emitted out of the nucleus, right? As a beta particle. So what is going to happen is that the proton number of that unstable nuclei actually increases by 1. However, the mass number remains the same because the neutron actually turns into a proton, which doesn't account for any difference in the mass number. So a beta particle is a fast-moving electron, which is notated like this. Right? So it's either 0, negative 1 E, represents the electron, or 0, negative 1 beta. Good? Now, why 0 is because it has no mass number, meaning it is not made up of a proton nor a neutron. Good? Why negative 1? Because this, as we know, this location is where we put protons. However, electron is the negative charge of a proton, so it is actually negative 1. Good? So it's negative 1, 0, E, or negative 1, 0, beta. Good? So that's how the notation of a beta particle. So it is, what we learned is a fast moving electron that can be emitted almost to the speed of light, and it can be blocked by metal foil, and it can travel a few meters in air, right? So that means it can travel even further than an alpha particle. It has a weaker ionizing power than alpha particle, meaning that as it passes through other atoms, it can just push a few of those electrons on the valence shells and cause them to turn into ions, right? Right, and then the final one is gamma ray. Good. Now, what happens in gamma ray is that a gamma ray is an electromagnetic radiation emitted from the nucleus, and it can also be referred to as a high energy photon. Right. A different textbook is going to say it's an electromagnetic radiation of very high frequency and short wavelength. Good. So what we're going to find out about gamma radiation is that it occurs after either a beta decay or a alpha decay. Now what happens is that the daughter nuclide that is now formed is in an excited state, meaning that it was unstable, is now give up its unstable particle, but it still has a lot of energy, right? So it wants to cool down, or calm down. In order to calm down, it must give up that excess energy, and therefore that energy that is given off is what is referred to as gamma radiation. Good. So it is just pure energy. It has no mass, it has no protons, it has no neutrons, nothing. It is just raw energy. Good. And what you're going to find out about gamma radiation is that it has no electric charge, and it can travel very long distances in air. And yes, that it has no effect on or the electric field and the magnetic field has no effect on it. Good. So its notation, right? It's 0, 0, and gamma. All right. So these are the notations of the three radioactive emissions. Okay. All right. So the final thing that we're going to look at um, for now is looking at the balancing equations. How can we balance equations as it relates to radioactivity? Now, what we're going to know is that once we have a unstable nuclei, that it over a period of time it can regain its stability by emitting a radioactive particle. Good. So it follows with this equation or chemical reaction here that it shows that an unstable parent nuclei, that nothing needs to be added to it. It just by itself is that it's going to give off a reaction. This arrow shows a reaction, and then what is formed is it's going to have a more stable nuclei formed, which we call it a stable daughter nuclei. And also, what we must account for is the radioactive emission, whether it is an alpha particle, beta particle, or gamma. And then also energy is given off, or energy is produced. Good. Now, one of the things that we must learn about this is that the left side of this equation must be equal in terms of numbers to the right side of this equation, everything on the right side. Good. So it means that the total proton number in our nuclear notation of the unstable parent nuclei on this side must be equal to the sum of all the proton numbers of the nuclear notations on the right side of the equation. Good. Same thing for the mass number for the unstable parent nuclei on the left side must be equal to the sum of the mass numbers on the right side of our notation. Okay. So for instance, the first type of emission was alpha emission. We want to understand what happens there when we have an alpha emission. So now, we see here, the notation for an unstable parent nuclei is AZX. Good? And that the reaction arrow, and then it gives off an alpha emission. So we know alpha emission is 42He. Right? So when we know this, see this, we know that is an alpha emission. That it is going to create a stable daughter nuclei. Right? Whether it creates a son or a daughter, it doesn't matter. Right? So it creates a stable daughter nuclei. Now, and then energy. As I mentioned before, is that the mass number on the left side must be equal to the sum of the mass number on the right side. So basically, 2 plus a given number must be equal to Z. So 2 plus what is going to be equal to Z? So we realize it's Z minus 2. Because what we're saying is that this element X is going to lose 2 protons. So it is going to be 2 protons less than X. So that's why this number must be 2 values less than Z. Good? An example is if you have thorium and, uranium. And that uranium, let's say unstable uranium, that will be 238, right? And that it gives off an alpha particle. So, as it gives off an alpha particle, it's going to form thorium. Good? Now, in our syllabus, you don't have to worry about knowing these symbols. These symbols will be given. Alright? Now, it's going to form thorium. So what you're going to realize that 92, that 2 plus what number is going to be equal to 92? 2 plus 90. So you realize that the mass number is going to be 90. So if you notice, we said that it was Z minus 2. Whatever Z was, that was 92. 92 minus 2 is 90. Good? Same thing we want to do here. We want to say what will be the mass number for the stable daughter nuclei. And you see that the mass number is going to be losing 4. It's going to be losing 4 nucleons. So therefore, it's going to be 8 minus 4. So 238 minus 4 is 234. And what we can do, we can trace back. 90 plus 2 is 92. Good? 90 plus 2 is 92, and 234 plus 4 is 238. And that is all you need to know for balancing equation for alpha decay. We're going to see the difference now with a beta decay. So as I say, beta decay now follows the same concept. Formula remains the same. Unstable parent nuclei. Reaction gives off a radioactive emission and creates a stable daughter nuclide plus energy. So in this case, our unstable parent nuclide is AZX. Good? It gives off a beta emission. So what we're going to see here, the mass number for this is 0. So 0 plus what number is going to give you 8? And you're going to realize that it's the same value. 8 plus 0 is 8. The mass number doesn't change. Now in this case, we're saying that an electron is given off. And if you can remember when I said that the electron comes from a neutron giving up its negative charge and turning into a proton. So therefore, the proton number increases by 1. And we can see that. So we want the total proton number on this side is Z. So therefore, if we have negative 1 plus what number is going to be equal to Z? And that will be Z plus 1. Because minus 1 and plus 1 cancel out, giving you back Z. Right? So an example of that is if we have, let's say, carbon 14. Right? So you know carbon 14 is an unstable is an isotope of carbon 12, right? So it is going to, let's say it gives up a beta particle. Right? Now we're saying that the mass number doesn't change. So the mass number of the daughter should be 14. Still 14, because 14 plus 0 is 14. Next, we're saying that a number when added to negative 1 is going to give you 6, and which is 7. 7 plus minus 1 is 6, or 7 minus 1, 6. So the seventh element is, as we know, is nitrogen plus energy. Good? Now in this case, what we're going to realize is that gamma radiation, it follows the same concept. And gamma radiation can follow right after a beta emission or gamma emission. So in this case, what we're going to realize is that it can give off there's with gamma radiation there is no change to the element. Good, it was just in an excited state, and now it is just would have lost some energy, so it can give up its energy there and still be the same element. Good. So that concludes it for now, where we look at the introduction of radioactivity decay, or physics of the atom. What we will go on to next is looking at answering of some questions, and then look at radioactive decay. Thank you for joining.